Hello everyone, and thank you for your attendance. I am Ruben Recabarren, and I will be presenting toward uncensorable, anonymous and private access over Satoshi blockchains. This research is a joint effort with my advisor Bogdan Carbunar from the Casper Lab at Florida International University. In this paper, we looked at the censorship problem where a client's access to the internet is monitored and disrupted by a resourceful censor. The censor has global monitoring capabilities, which means they are able to perform global traffic correlation and identify communication exchanges of even the most advanced censorship-resilient systems, such as Tor. In addition, we consider that these powerful sensors only have full disruption capabilities within the censored regions, which means outside publishers cannot be targeted for disruption. Unfortunately, even this partial disruption capability is enough to completely censor data access because the censor only really needs to disrupt one communication endpoint. To solve this problem, we use cryptocurrency blockchains. This is not a novel approach. However, most existing solutions use blockchains that provide very little collateral damage, use embeddings with inefficient cost schemas, or are simply not scalable enough, as I will show in the following slides. Instead, we use what we call Satoshi networks. These networks include cryptocurrencies such as Bitcoin, Litecoin, Dogecoin, and many others. We chose to study these Satoshi blockchains because they currently have the largest market capitalization, and so they potentially represent the largest collateral damage to would-be censors. So in summary, our solution UWeb builds on top of Satoshi networks and blockchains and aims to provide uncensorable anonymous access even in the presence of an adversary able to perform global network traffic correlations. However, in order to achieve this, we need to overcome several challenges. First, we need to satisfy Satoshi blockchain constraints. Otherwise, we can't even participate on their network. As mentioned, we also need to improve the writing throughput and goodput of previous writing solutions at a reasonable cost. And finally, we also need to provide a private and efficient data retrieval mechanism to access data possibly stored among millions of transactions. Now, Satoshi blockchains impose a suite of constraints. Some of these constraints are public knowledge, while others we had to discover empirically during our experiments. For instance, the maximum allowed size of a transaction is 100 kilobytes, while the maximum size of a block is 1 megabyte, ignoring segregated witness. We also need to take into consideration restrictions on the number of inputs and outputs, confirmation times, length of unconfirmed transaction chains, and even minimum transaction fees. These are only examples of the constraints that we had to consider, but we perform a more thorough constraint documentation on our paper. Another important challenge that we need to address is to develop blockchain writing solutions that have high throughput and goodput. For this research, we define throughput to be the size of data made available on the blockchain per unit time. Similarly, we define goodput to be the ratio between the total size of embedded data to the total size of the transaction construct. As we can see in this table, most existing solutions either can only embed a few bytes per transaction, have low goodput and throughput, or have a very high storage cost. One exception to this is Titanus, our previous work. However, Titanus can only embed 1600 bytes in a transaction around and has a relatively small throughput and therefore lacks the desired scalability. To address these challenges, we introduce max-rate transactions. A max-rate transaction consists of a funding transaction with one input and 2,937 outputs, which is the maximum allowed. One of these outputs sends the remaining balance to the writer's wallet, but each of the other 2,936 outputs fund an input in a spending transaction, where each input script stores up to 1,568 bytes of data. Now, each of these spending transactions has 59 inputs, which again, it is the maximum allowed, and so a funding transaction funds up to 49 spending transactions. As a consequence, the goodput of this max-rate construct is about 4.6 megabytes. Also notice that we are able to send this whole construct after only one confirmation boundary. That is one mining epoch. Effectively, this means we need to confirm the funding transaction before being able to send the 49 spending transactions all at once. The peer-to-peer cryptocurrency network then takes care of broadcasting our data to all standard compliant participating nodes. It turns out that the max rate construct is generalizable and it actually provides the scalability that we're looking for. The main observation here is that we can always use preparing transactions to unlock a maximum number of funding transactions in one confirmation boundary. This design achieves a maximum number of transactions to be sent to the network without limitations from the number of unconfirmed transactions. However, we are still limited by the size of the block, network congestion, and so on. As a consequence, in this case, the second confirmation boundary does not line up with the second mining epoch. Nevertheless, as soon as some of our funding transactions get confirmed, we can start sending the corresponding portion of max rate transactions all at the same time. As you can see, after only 2 confirmation boundaries, we are already at 13.5 gigabytes of maximum Goodput. Now we have used max rate transactions to build the UWeb storage system only. However, we still need a mechanism to organize this content for easily retrieval and reconstruction. For this, we designed the special types of transactions that index the persistent content. Each block shown here is stored in a transaction, and UWeb supports several types of content stored in transactions. All content stored is signed and can also be encrypted if desired. First, dir entries correspond to directories or files that store content. All UWeb content is stored under a root directory controlled by the content publisher. OP transactions allow publishers to add other directories or content. For instance, this OP entry creates a directory for Alice, and this other one creates a directory that will store public key certificates. Now, under Alice's directory, one can store files and also as dir entries, and these dir entries store the ID of the max rate transaction that stores the content. In addition, OP transactions can also be chained to allow content producers to sort of modify their content. Explicitly, OP transaction chains can store a historical log of content modifications made across time. For instance, this transaction points to an updated content for file F that consumers can similarly search for and reconstruct. Now here is the same table that I showed before, including the UWeb results. It turns out that UWeb's max rate transactions achieve a payload that is about 4 orders of magnitude better than Titanus, which is the current state of the art, and also achieves a writing throughput of about 3 orders of magnitude better than the state of the art. A more detailed treatment of these results can be found in our paper. Now, we also performed several experiments, all of them on the real Litecoin network. We use Litecoin because its network is equivalent to Bitcoin. However, the much lower cost allowed us to make a better use of our limited funding. In the following slides, I will only cover our longitudinal newsfeed writing and blockchain stress test experiments. However, we include more details and simulation results in the paper. In the longitudinal newsfeed writing experiment, we published an average of about 400 BBC articles per day for 134 consecutive days. In total, we published around 53,000 articles with a total size of 51 megabytes and a total cost of around half a Litecoin. In this graph, we have plotted the first confirmation time versus cost and size of the published data. Darker dots mean larger and more expensive publications, and we can see that these darker dots are all over the place, which means that the cost of writing does not have a significant impact on the time to first confirmation. In fact, this graph suggests that confirmation time may be more dependent on other factors, perhaps like network congestion rather than cost. For the blockchain stress test experiment, we packaged 41 censorship-resistant tools, including source code for Tor, Stegosaurus, and many others, and published them on the Litecoin blockchain. In total, we persisted 217 megabytes of code for a total cost of 2.5 Litecoin. We sent the 3 largest projects with a total of 140 megabytes in the same UWeb content push, and sent the rest of the projects in 2 different pushes on different dates. And we did this to have a better control over our experiment impact. The 140 megabyte experiment lasted 7.6 hours from the first unconfirmed max rate transactions that we sent and observed in the mempool until the last one received at least one confirmation. This graph shows the violin plots confirmation times during and before our experiment. We measured confirmation times for transactions of several fee rates. We can see that confirmation times for financial transactions are essentially unimpacted. Thus, this graph suggests that large-scale writing in the blockchain has no impact on financial transactions of any fee rate. However, max rate transactions do experience a significant delay of up to 27,000 seconds. Another interesting metric that we captured was the impact of our system on the network's mempool. This graph shows the timeline of the mempool size in terms of the number of transactions and total byte size during our 3 writing operations. We split our experiment in 3 phases to better control the impact over the network. Our experiments generate substantial spikes in terms of both number of transactions and total mempool size. However, the mempool is vacated linearly, which implies that higher fee transactions get prioritized correctly and our actions do not produce a degradation at current network usage levels. So on the previous slide, we saw how our system does not interfere with financial transaction confirmation times. And in this slide, we have shown that in practice, our system does not disrupt the underlying cryptocurrency gossip network. So thus, we have effectively covered all relevant areas of impact that our system could have influence on. In conclusion, we have shown that UWeb improves the state-of-the-art data writing techniques in commercial Satoshi blockchains. UWeb also provides private access to hard-to-censor content. We have shown results of large-scale writing experiments, and we have shown that our techniques have very low impact on the cryptocurrency ecosystem. And with that, I will now take any questions that you may have.